Hello, everybody. This is Sunday. It's April 10th, and we're heading into week 13 of our online astronomy course. And before I get to talking about anything else, I want to let you know that as we approach the end of the semester, I know things get really busy for you. And for that reason, I'm opening up all of the final assignments. I'm opening up the final exam, I'm opening up the constellation quiz, and I'm opening up your signature assignment. And so you can do those at any time you want. All of the rest of the course materials are open for you. So if you want to finish early for some reason, you're welcome to. If you want to finish at the scheduled time, you're welcome to. So do that however you like. And I'll be sending out an email Monday morning about this and give you more information about what I just said about the end of the semester. All right, so we are going to be talking about, in Module 13, galaxies. And there are a huge number of galaxies in the universe. There are as many galaxies in the universe as there are stars in our own galaxy. You know, several 100 billion galaxies that we know of. So it's an incredible universe filled with galaxies. And this picture behind me is a Hubble Space Telescope picture of a cluster of galaxies. So this is an actual photo. This isn't some montage that was put together just throwing a bunch of galaxies together. This is an actual photo of a lot of galaxies out in space. And the first thing you'll notice is that they have different shapes. And let's take a look at those. I'm going to move over to the side here just a little bit. There we go. And some galaxies have a spiral shape, like our own Milky Way has a spiral shape. And you can see that just right over my shoulder here is this galaxy. And you can see has spiral arms winding itself out from the center. Now, there are also elliptical galaxies, and elliptical galaxies are a big football of stars. And you can see elliptical galaxies are really common in this galaxy cluster, and you can see them all over the place. Here's one, and here's one up here, and here's a bunch over here. And so there's a lot of elliptical galaxies in this. There are also irregular galaxies, galaxies that have some weird shape, and they really don't fit in with anything. And maybe you can see some of those here. If I look, there are some galaxies that just sort of look strange, like up here, right there, there's a strange looking galaxy. And these are irregular galaxies. Now we have two irregular galaxies orbiting our own Milky Way galaxies. They're called the Magellanic Clouds because when Magellan saw them as he sailed south to go sail around the world, he saw these in the sky, and today they're called the Magellanic Clouds. They're not clouds, they are irregular galaxies that are circling our own Milky Way galaxy. Now, spiral galaxies, I'll move to the side again. Spiral galaxies actually come in two types. There are regular spirals that just have sort of a flat disk and spiral arms coming out from the center. And then there are galaxies that have a bar in the center. Like right here, this galaxy seems to have a bar going across that galaxy. And then the spiral arms come out from the end of the bar. So some galaxies are just regular spirals, some are barred spirals, some are elliptical, some are irregular. And our Milky Way is actually a barred spiral galaxy. So there's all sorts. And how do we know how far away these stars are? We use Henrietta Swan-Leavitt's period luminosity relation, the Leavitt law, to find the distances to Cepheid variable stars that are in those galaxies. And that allows us to find out how far all of these galaxies are away from us. And you'll be doing some of that on your homework quizzes. And also, excuse me, it's really fascinating because we can also look at these galaxies, and we can see that some of them appear to be very close together. And there's some galaxies on here that are actually interacting with each other. Like right here, there are two galaxies that are interacting with each other. They're colliding. As I talked about last week, when two galaxies collide, the stars don't collide because the stars are so far apart, but the gas between the stars collides. And that can cause some fireworks, some star formation, bursts of star formation inside those galaxies. And sometimes one galaxy can actually devour another galaxy. And we can find examples of that, lots of examples of that. That's fairly common. And it's called galactic cannibalism, where two galaxies merge into one. And so that's pretty cool. So that's how galaxies evolve, how they start out as a huge cloud of gas and dust. And as they collapse, some change into ellipticals, some become spirals, some become irregulars. And what happens is that they tend to form little parts of galaxies, and those little parts of galaxies come together. So it might be the cloud collapses and globular clusters of stars form, and then they fall together, and so on. So how galaxies form is becoming better understood. And in just a second, I'll tell you an important ingredient in galaxy formation. Now, as I said, we can tell the distances to these galaxies by taking a look at Cepheid variable stars in those galaxies. And we can also look at the Doppler shift of their spectral lines to find out how fast they're moving. And it was around the 1920s that Edwin Hubble discovered that except for the very nearest galaxies, that all the galaxies in the universe are moving away from us, getting farther and farther and farther away. And furthermore, he found out that galaxies that were twice as far away from us are moving away from us twice as fast. And you can sort of picture this as an expansion, because if you imagine you're baking a loaf of raisin bread, and you get the dough all ready, and you toss in some raisins, and you mix it around and put it in the oven, and the bread begins to rise. What happens is that all the raisins in that bread, as the bread rises, move away from all the other raisins. And so as the bread expands, all the raisins are carried away from all the other raisins. I can show that to you in another way using this chain of rubber bands that I've linked together. Here are 4 rubber bands, and you can imagine that the ends of the rubber bands, like at this end over here on the left side of your screen, where I'm holding it as a galaxy, and each of the knots is a galaxy. Here's a galaxy, here's a galaxy, here's a galaxy, and where I'm holding it over here is a galaxy. Now I'm going to hold this galaxy right here over on the left side of the screen. I'm going to try to not let that move, past the left side of the screen. And we're going to watch what happens as the universe expands. This galaxy of universes, this universe of galaxies expands. So I'm going to pull out my right hand while keeping this left hand still, and watch how the knots move. Watch how the galaxies move. So here we go. And the universe is expanding. And you can see that all of the knots are moving away from our galaxy right here, the Milky Way. That's over on the left side of your screen. So let's watch that again and notice how far and how fast the knots move. And take a look at how the other knots move as this knot moves from about the center of your screen over to the right edge. So let's watch that. Here we go. And the galaxies expand. And you notice that this galaxy that was farthest from our Milky Way traveled the farthest distance. but they all move that distance in the same time. So that means that this galaxy here was moving faster. In fact, galaxies that are twice as far from the Milky Way over here on the left, these nuts that are twice as far away are moving away from this hand twice as fast due to the expansion of that rubber band. Watch it again. See how fast those nuts are moving. So that's why we say the whole universe is expanding. There's no galaxy in the middle, because if I did this, and instead of holding the rubber band here or here, let's say I moved in a nut and held it here and then expanded, well, you'd see the same thing happen from this nut. So every galaxy sees the same expansion of the universe. There's no galaxy at the center. So the universe is expanding. Great, great discovery by Edwin Hubble. And you'll learn about Hubble's law that talks about how fast galaxies expand away from us, I should say. And it turns out that that if you keep in mind the number 70, it turns out that for every megaparsec, million parsecs, 3,260,000 light years, for every million parsecs, for every megaparsec, a galaxy is away from us. It moves away 70 kilometers per second faster. So a galaxy that's 1 megaparsec away moves away at 70 kilometers a second. A galaxy that's 2 megaparsecs moves away at twice that, 140 kilometers per second. And if it's if there's a galaxy 3 times as far away as that original galaxy was, it moves away 3 times as fast. 3 times 70 is 210 kilometers per second from us. So the Hubble law is really an easy law to use, and to be learning about that. And what's especially cool is that if you look at some of these really old galaxies, and if you take a look here at some of these galaxies, look really red. These are very, very distant galaxies. And so we're seeing these galaxies because it's taken billions of years for that light to reach us. We're seeing those galaxies as they were billions of years ago, billions of years in the past. And so telescopes are time machines. We can look at the past universe. We can look at the universe as it was when it was only a couple billion years old, you know, when it was only a seventh of its present age. And we can watch it evolve by looking at light that's closer and closer and closer to us. You know, in biology, to find fossils, to find what past life looked like, you have to dig up fossils and figure out what the creature was that those fossils came from. No, in astronomy, we can watch it happen because we can look at very, very, very old light. Also, I'll tell you that there are clusters of galaxies. The galaxies come in clusters. And our galaxy, our Milky Way galaxy, is a member of a cluster called the local group. You are all members of the local group. It's called a poor galaxy because there's only a few galaxies in there, a few meaning around 40. But there are very rich clusters of galaxies, like the one you see here behind me, that have a huge numbers of galaxies in them. And those clusters of galaxies are arranged in superclusters of galaxies. And those superclusters of galaxies are arranged as though they were on the surface of soap bubbles. And so the galaxies in the universe are arranged like they were on the surface of soap bubbles. And inside the soap bubbles are almost no galaxies, huge cosmic voids. And so we're learning more and more about all these cosmic voids. And finally, if we take a look at how galaxies move in galaxy clusters, if we look about how stars move in star clusters, we find out that there's not enough visible mass to provide the gravity that holds those clusters of galaxies or clusters of stars together. And that means that it has to be some matter in the universe that isn't shining. And we don't know what it is. We really have no idea what it is. It's hard to study because we can't see it, but we can study it only by its gravitational effect on other shining objects. For instance, we know that our Milky Way galaxy is surrounded by a halo of dark matter because stars on the outside of the galaxy are orbiting the center a lot faster than they should be if all the mass of the galaxy was just at the center. So you learn about that, and you'll also learn about active galaxies. Some galaxies give off huge amounts of energy. Those aren't in today's universe for the most part. We have to look at the most active galaxies in the past when we look at very old light. And those are called active galactic nuclei. Because what's happening is that in the centers of these galaxies, in the central nucleus of these galaxies, there's a supermassive black hole. Now, you already learned about how there's a supermassive black hole at the center of our own Milky Way galaxy of around 4 million times the mass of the sun, 4 million solar masses. But for these active galaxies, that supermassive black hole has a mass of millions, billions, or even trillions of suns. And so that is a powerful gravitational energy that causes those active galactic nuclei to emit lots of energy that we can study. And you'll be learning about that as well. So you'll learn about what we can see, all these galaxies, and you'll learn about what we can't see, dark matter. And don't think dark matter is just a small part of the universe. There's 6 times more dark matter in the universe than there is regular matter, the sort of stuff that we are made of. So I hope you enjoy learning about galaxies in the universe. Next time we'll end and talk some more about how the universe itself has evolved. And we'll also learn a little bit about the search for extraterrestrial life. So that is in module 14, but I hope you enjoy learning all about galaxies. And as always, if you have any questions about this material, you can send me an email. You can be happy to set up a Zoom conference, or you can come to my office if you'd like for a meeting. But have a great week. Learn all about this. And remember, anytime you want to now, you can take the final exam, you can take the constellation quiz, and you can take the signature assignment. Please don't forget about that signature assignment because it's worth half a letter grade. And sometimes people just sort of blow it off and it really hurts them. So the signature assignment is short. You can do it easily in 15 minutes. And all you have to do is answer a question, which is, how do astronomers think about the universe? If you write just a short couple of paragraphs about that, any answer you give me is fine because I want to know what you think. And that'll work great for your signature assignment. So good luck. And I will look forward to talking to you next time. Oh, wait. Almost forgot about stellarium. Got to pull up stellarium here. Almost forgot about stellarium. So let me pull up the screen. There we go. This is what the sky is going to look like on Wednesday night. This is Wednesday night. And if you take a look, I'm sorry, this is, in fact, this is Tuesday night. And we're looking southeast in the sky. This is around 9 in the evening, and there's the moon. And the moon is in the constellation of Leo up here. Leo looks like this backwards question mark. That's the head of the lion. Here's the body of the lion. The moon's in Leo. And what's going to be happening, let me put up Leo there. There's the lines that make up Leo, his head, his body. There's the moon. And I can put up the figures too, because I enjoy doing that. And once again, the moon has entered Leo. And over the next couple days, 13th, it's leaving Leo. It's about to enter Virgo. 14, 15, 16th. 16th, there we are at 9 o'clock. The moon's going to be very low in the east at this time because this is the full moon rising on the 16th. So again, have a great week and look up at the sky. It's beautiful out there. And I will see you later next time. Bye-bye.